welcome to Physics 2120. This video is going to be about Coulomb's law, which is a law you'll be using a lot in this course. Some of your more difficult homework problems will come from this law. Now, Coulomb's law in itself is not that complicated. Coulomb's law says that the force between two charges, here's a positive charge and here's a positive charge, the force that pushes this one that way and this one this way is a constant, K, times charge 1 times charge 2 divided by the square of the distance between them, also known as the radius. Now you have to keep in mind when you use Coulomb's law that the charge needs to be in coulombs. Usually you will not be dealing with coulombs of charge. That's a whopping load of charge. You'll be using microcoulombs or nanocoulombs or sometimes even picocoulombs. So if that's confusing to you, you'll probably want to review your prefixes. But just remember when you do this, for this to work, because the constant is Newton meters squared per coulomb squared, your radius needs to be in meters and your charges need to be in coulombs. Now, an important thing to keep in mind is that Newton's third law still holds, even though we're not talking about falling objects or gravitation. What we're talking about now is the force between two charges, but even so, this force, force 1, 2, which is the force of charge 1 on charge 2, and points that way, has got to be exactly equal and opposite in direction to force 2, 1, the charge of charge 2 on charge 1, pointing this way. So that's an easy test question, something to remember. Now, if we think about charges in general, and let's think about charges in a line, like linear charges in this case. If we have charge 1, charge 2, and charge 3, three charges, all of them positive. If we were to just let them go, you can imagine what would happen. If we let them loose, these two would fly off this way and this one might sit in the middle. But we're going to play a game. We're going to pretend like I've got like a hammer and just bang, 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 and I'm going to nail these two down. So I'm really not worried about what forces are on these because these aren't going to move. I want to know what kind of forces will be on the one in the middle. And again, you'll have homework problems like this. So, the force 1, 2, the force of charge 1 on charge 2, because they're both positive, they'll be pushing each other away. And so that charge will be pointing this way. Now, charge 3, acting on charge 2, force 3, 2, is also going to be a positive charge, so it pushes the other way. And if all these charges were the same, and if these distances were the same, then you can see how this one would just sit here, being pushed by both sides. Kind of like a tug of war, like you had in elementary school, where the forces are the same on both sides so he doesn't move. If this charge got a little bigger, it would push it this way for a while, and then it would stop. Because as it gets further away, the force becomes less and less. And that has to do with the inverse square law, which we'll have another video on. Now, these are three positive charges in a row. So you can imagine, what if instead we have a positive charge, and a negative charge? Now again, keep in mind how we're using Coulomb's law. We have radius 1, 2. That's the distance between charge 1 and charge 2. We have the charge 1 and charge 2 themselves, both positive. And so force 1, 2, the force of charge 1 on charge 2, because they're both positive, will be pushing this way. But charge 3 is negative. So instead of pushing it, it's pulling it. You know, like charges repel, opposite charges attract. And so again, we're going to make sure these don't move, and we're going to see what happens to this one. Well, you can see that since both of the charges are now pointing in the same direction, it's not going to sit still like it did here. It's going to take off and it's going to move, and it's just going to keep speeding up as it goes. Now this is for linear charges, and some of your first homework problems will be on linear charges. But, and I said before, Coulomb's law is going to get a little complicated when we get to charges that are nonlinear. So let's take a look at these three charges right here. Charge 1, charge 2, charge 3. Again, we're not going to let charge 1 and charge 2 move. We're not, yeah, are there forces between charge 1 and charge 3? Yeah, there are. But we're not interested in that. We're just interested in how these two charges are affecting this one right here in the middle. So again, we've got radius 1, 2, from charge 1 to charge 2, and radius 3, 2 right here. Because everything's positive, force 1, 2 will be pointing in this same direction, along the same line as the radius, but it's going to be pointing down a little bit. And then along this line, force 3, 2, the force of charge 3 on charge 2, will be pointing upwards. And so if we want to add these vectors together, I hope you've already studied vector addition, but if you haven't, we will have a review. An easy way to figure out what the total push would be is something called the parallelogram method, which basically says turn it into a box, a mirror image of this box right here. When we add these two charges, these two forces together, we would get a total force pointing in this direction. And that's an easy way to get a conceptual idea of what this total charge would look like, total force would look like. This is the total force. And this little epsilon just means add it all up. So you can see how the total force on this one would not be as great as it was if these were closer together or near, but the total force will push in this direction. Now, to add these two forces, to actually figure out a numerical answer for what is the total force and in what direction is it pointing, we'll have to go to another video on vector addition.